Introduce HAADF-Segment, a hackathon project for the automated analysis of atomic scale electron microscope images. 2D materials are strongly affected by defects in their crystal structure. Luckily, we can image these materials at an atomic scale, but manual defect identification is slow, error-prone, and unscalable. Therefore, an automated machine learning-based defect classification pipeline would enable faster data-driven material analysis. Monolayer TMD alloys are one promising 2D material for next-generation electronic devices. HAADF-STEM is a technique that allows us to image these materials at an atomic scale. The goals of this project are to use this STEM data in order to reliably detect defects in a quaternary TMD alloy. We also aim to classify the types of defects and analyze defect statistics. For the supervised learning approach, we implemented a UNet architecture neural network based on the Atom AI framework in order to segment the HAADF-STEM images into the 5 distinct atomic species. And this achieved good performance with an F1 score of 0.94, which demonstrated that the model was able to use the intensity differences in the image to classify the atoms.
And this approach we worked on is our physics-informed Atom AI classification pipeline. We start from high-resolution STEM images and apply SVD filtering to surpass noise while preserving atomic contrast. Atomic positions are detected and atom-centered patches are extracted and rotationally augmented. We use weak supervision with Gaussian mixture models on atomic intensities to label A sites as MO or W and B sites as S2, SSE, or SE2, enabling scalable training. An Atom AI CNN is trained for 5-class atomic classification with randomized evaluation. Without constraints, accuracy is about 75%. By enforcing lattice-valid predictions, accuracy rises to 94%, and the same framework enables automatic vacancy detection. This combines deep learning with physics to produce reliable atomic classification and defect discovery.
Additionally, we implemented various unsupervised learning approaches, including PCA and UMAP, in order to identify regions of the images that were anomalous. We also implemented a self-supervised audio encoder on the stacks of images in order to quantify atomic instability in images taken over time. In this hackathon project, we validated various supervised and unsupervised machine learning pipelines for the automated processing of HAADF-STEM data. The segmentation using UNet achieved a maximum F1 score of 0.94 when classifying atomic species. Future work will involve generalizing the model to other 2D materials and other TEM acquisition parameters. Now I'll just switch to a quick demonstration of the software. Based on the supervised framework, we can now load DM3 files just like this and run the segmentation in defect discovery, which will segment each of the atom types in the image based on the UNet. And this will display the distribution of atoms that are in the loaded image, as well as detect potential sites for defects, such as isolated point defects or this cluster of defects here, which may correspond to a different phase.